weight must we add to D in order to make it to be in equilibrium? Solution. Looking at the diagram, we are told that the beam is on a fulcrum of 1.5 meter AB and BD, and the weight of the beam is 10 newtons on the fulcrum. Then we are now given that at a point A, a weight of 30 newton is hung 1.5 meters from the fulcrum, and the weight of 5 newton is hung at D, which is 1.5 from the fulcrum, and a weight of 20 newton is hanged at C, that is 1.2 from the fulcrum, and we are told that the weight of the rule is 10 newton resting on the fulcrum. Clockwise moment is equals to anti-clockwise moment. So we have that 30 newton, taking the anti-clockwise moment, which is 30 newton, times the distance from the fulcrum, which is 1.5, is equals to 20 newton of the weight hang at the point C times 1.2, that is the distance of that 20 newton from the fulcrum point, that is 1.2, plus the weight at D, which is 5, times the distance from the focal point, which is 1.5. We now have at the anti-clockwise moment we have 45, which is equals to 31.1. It turned anti-clockwise. Since the beam weight rests in equilibrium horizontally, therefore 20 times, in order to add the weight, what weight will be added to raise the beam? 20 times 12, that is anti-clockwise moment, taking moments still at that point, 20 times 1.2 plus the weight added, which is 5 plus that weight times 1.5 is equals to 45. 24 plus, that is times 1.2 with 20 will give us 24, plus 7.5 is 1.5 times 5 plus 1.5 W, which will give us 45. Then summing up the like terms, we have 31.5 plus 1.5 W, which will give us 45. Collecting like terms, we have 1.5 W equal to 45 minus 31.5. 1.4 W is now equal to 13.5. Our W, making W the subject of the formula, we have 13.5 over 1.5, which is now equal to 9 Newton. Example 8. A uniform beam AF having 80 Newton at point A, 0.6 meters from the fulcrum B, having a reaction R1 and another mass of 300 Newton hanged at C, point C, 1.2 meters from the focal point B and 1 meters from the fulcrum point D, having a reaction of R2. Another 100 Newton having a distance of 0.5 meters from the fulcrum D. In the diagram above, we are asked to find the reaction R1 and R2. Solution. Summing up the reactions and the weight together, we have R1 plus R2, which is the two reactions, equals to the weight of the which is acting on the beta rule, which is 80 plus 300 plus 100. Therefore, R1 plus R2 is equals to 480. This will be our equation 1. Anticlockwise moment equal to clockwise moment. Then, taking our reaction at the point R, or the reaction R, we have that 300 Newton at the point C is covering a distance of 1.2, which is going which is the clockwise moment plus times 1.2, which is the distance from the force 300 to the focal point B, or R1. Then another 100 Newton force, it's going clockwise too, times the distance from E to B, which is 0.5 meters plus 1 meters plus 1.2, which will give us 2.7 meters. Then plus another reaction, which is equal to the anticlockwise moment, which is 80 Newton times 0.6 meters from the reaction R1, and the R2, which is not known, which is going anticlockwise, times the distance from R2 or dB, which is 1 plus 1.2. Then we have 360 plus 270 is equals to 48 plus 2.2 R2. Summing up, we have 630 is equals to 448 plus 2.2 reaction. 430 minus, collecting like terms together, you have 630 minus 48, which is equals to 2.2 R2. Subtracting, we have 582 is equals to 2.2 the reaction. Therefore, making the R2 the subject of the formula, we have 582 over 2.2, which will give us 264.5 Newton. From the equation 1, we have that R1 plus R2 is equals to 480. For substituting the value of R2, we have R1 plus 246.5, which is equals to 480. Making R1 the subject of the formula, 264.5 crossing over will become minus. Subtracting the values, we have 215.2 Newton, or sum of force anticlockwise and clockwise direction is equal to 0. Therefore, minus 8, that is the reaction at the point, is times 0.6, that's the distance from the reaction, 0.6 plus 300 times 1.2 minus R2 times 2.2, which is the distance, the reaction from the reaction, times 100 plus 100 times 2.7, which is not equal to 0. If we make the computation, we still have our R2 equals to 264.5 Newton. Example 9.